Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to visualize a really sprawling modern architectural marvel, like a massive glass and steel house perched right on a cliffside.
Okay, I can picture that.
Yeah, and it has this incredibly complex foundation, right? Vaulted ceilings, a heavy slate roof. But there is a structural reality to this house that totally defies everyday intuition.
Which is?
85% of the load-bearing columns, the rebar, the absolute core of its structural integrity, is completely invisible.
Wow. Okay.
You can't touch those columns. You can't, bounce light off them. But the mathematics of tension and compression absolutely dictate they have to be there.
Right, because otherwise the whole thing comes down.
Exactly.
Yeah.
If you were to somehow cleanly extract that invisible scaffolding, the entire cantilevered structure would just instantaneously succumb to gravity and collapse into the ravine.
It'd be a disaster, yeah.
And that structural dynamic, that is the baseline, non-negotiable reality of how we understand our universe. Specifically, it's the foundational rule of galactic dynamics.
Because galaxies are held together by this invisible, non-baryonic scaffolding, what we call dark matter.
Right. But then, imagine you are mapping out a seemingly quiet cosmic neighborhood, and you stumble across an absolute architectural impossibility.
You find a house floating perfectly intact.
Yes. Stable, entirely fully built, without a single one of those invisible load-bearing columns.
Which, that forces a total reevaluation of the engineering principles you thought govern the universe, right?
Totally.
Finding a structure that shouldn't exist doesn't just mean the structure is weird. It means your foundational equations regarding cosmic architecture have these spectacular, violent exceptions that we're only just beginning to comprehend.
And that brings us to the monumental data published in April of 2026. Okay, let's unpack this, because astronomers Mike Leakine and Peter Van Dockum and their collaborative team at Yale University just dropped an absolute bombshell.
They really did.
They confirmed the discovery of a third galaxy-designated NGC 1052 DF9, or just DF9, that appears to be entirely devoid of dark matter.
It's just incredible.
It is that cliffside house, completely missing its invisible columns, just sitting out there stable in the void.
And, the scientific weight of this really cannot be overstated. Finding a single galaxy missing its dark matter halo back in 2018.
That was DF2.
Right, DF2. That was treated by many as a statistical anomaly, or perhaps even an observational error.
People were definitely skeptical.
Highly skeptical. And then finding a second one shortly after, that elevated it to a real crisis for our theoretical models.
Yeah, crisis is the right word.
But confirming a third. And critically, finding that it perfectly aligns with the other two in a highly specific spatial and kinematic geometry, that isn't a glitch in the data anymore.
No, definitely not.
That is an entirely new class of object. It forces us to confront theories of galaxy formation that previously seemed, far too chaotic and hydrodynamically violent to be sustainable.
So we have an incredibly complex physical puzzle to unpack today. We are going to look closely at the exact mechanics of how a galaxy manages to actually decouple from its dark matter halo.
The uncoupling process is fascinating.
It really is. And we're going to examine the extreme physics of a high-speed supersonic cosmic collision that triggered this separation billions of years ago.
Right, the bullet dwarf scenario.
Exactly. And perhaps the most beautiful paradox of this entire discovery, we're going to explore how this highly anomalous galaxy, which is defined entirely by its missing dark matter, might actually serve as the final crushing mathematical proof that dark matter is a distinct physical entity.
Because we found a place where it was left behind.
Precisely, because we found the empty spot.
It's an elegant paradox, isn't it? To prove a substance is a physical reality rather than just, a mathematical tweak to our understanding of gravity, you have to find a scenario where that substance has been dynamically separated from ordinary matter.
You have to catch it in the act of not being there.
Yeah, exactly. But to fully appreciate the mechanics of DF9, we really need to look at the kinematic tension that defined the lambda CDM model in the first place.
Baseline expectation.
Right. We need to look at the baseline expectation for a galaxy's velocity dispersion.
Let's focus on that kinematic tension then. Because within the standard model of cosmology lambda, cold dark matter,
Yeah.
Dark matter isn't just some fringe component, right?
Not at all. It represents roughly 85% of the universe's total matter content.
So the baryonic matter,
Mm-hmm.
the gas, dust, stars, that's just the frosting.
Yeah, a very thin layer of frosting.
And the reason we know the cake is there, even if we can't see it, comes down to how fast that frosting is spinning.
That's a great way to put it.
Like if we look at the rotation curves of typical galaxies or the velocity dispersion of stars within dwarf galaxies, the math just fundamentally doesn't work if you only count the luminous matter.
It fails catastrophically. The foundational tool we use here is the virial theorem.
Okay, break that down for us.
So in a stable, gravitationally bound system, the kinetic energy of the objects moving around inside it,
The stars.
right, the stars, their kinetic energy has to be balanced by the gravitational potential energy holding the whole system together.
Otherwise, they just fly apart.
Exactly. If we measure the kinetic energy, which we do by observing the velocity dispersion or, how fast the stars are buzzing around relative to each other,
Right.
we can calculate exactly how much gravitational potential energy is required to keep those stars from exceeding escape velocity and just boiling off into intergalactic space.
So the velocity dispersion is really the key metric here.
Absolutely.
Because if I'm looking at a typical dwarf galaxy, the stars are moving incredibly fast. It's like watching a merry-go-round spinning way too fast. Right?
Yeah, violently fast merry-go-round.
The kids, or the stars, should be flying off. The centripetal acceleration required to keep those stars in their orbits is massive.
It is. And if we calculate the mass of the galaxy strictly by counting the starlight, adding up the mass of the gas clouds, the luminous mass.
Stuff we can actually see.
Right. The resulting gravitational binding energy from just that visible stuff is nowhere near enough to counter that kinetic energy.
The kids should be flying off the merry-go-round.
But they aren't. And the disparity is often an order of magnitude or more. I mean, in typical dwarf spheroidals, we see mass-to-light ratios that are astronomically high.
So you need invisible seatbelts.
Exactly, invisible seatbelts. The visible matter might only account for 10% or even 1% of the gravity required to keep the system virialized.
That's wild. 1%.
Yeah. The stars are moving with such high velocity dispersions that, absent some massive unseen gravitational anchor, the galaxy should have dissolved billions of years ago.
So the dark matter halo provides that deep gravitational potential well.
It is the anchor. Yeah.
Okay, so the baseline rule is firmly established. If you have a galaxy of a certain stellar mass, you absolutely expect its stars to be moving at a relatively high velocity because they are surfing inside this massive unseen dark matter gravity well.
That is the universal expectation, yes.
Which sets the stage perfectly for the absolute kinematic shockwave the Yale team triggered when they aimed their instruments at the constellation Cetus.
Oh, it was a massive disruption to the field. So we are looking at a field roughly 60 to 70 million light years away, dominated by a massive elliptical galaxy called NGC 1052.
But the focus isn't that central elliptical galaxy, right?
No, it's the highly unusual population of satellite galaxies surrounding it. The initial crack in the dark matter paradigm actually occurred a few years earlier in 2018.
Right, when Van Dokkum's team first identified NGC 1052 DF2.
Exactly, DF2.
And DF2 is categorized as an ultra-diffuse galaxy. And what's wild is they found it using an instrument that, frankly, sounds like it belongs in a commercial photography studio rather than a world-class observatory.
You're talking about the Dragonfly telephoto array.
Yes.
The Dragonfly.
It is a phenomenal piece of engineering, truly.
Why-
Born out of a very specific observational necessity.
Why did they need it? Why not just use Hubble right away? Well, traditional massive reflectors, like the Hubble Space Telescope or the Keck Observatory, they're unparalleled at achieving high resolution. But they actually struggle when it comes to mapping incredibly faint, low surface brightness objects spread over a really wide field of view.
Because of the optics design, right?
Yeah, largely.
Like if you have a massive primary mirror and a secondary mirror suspended in front of it, you introduce diffraction.
Exactly. You get light scattering off the microscopic imperfections in the mirror coatings or the struts holding the secondary mirror, which creates a kind of optical noise floor.
So it's like trying to see a whisper in a noisy room.
That's a perfect analogy. The internal scattering within a traditional reflecting telescope creates these broad wings on the point spread function of bright stars or central galaxies.
And that scattered light effectively washes out the exceptionally faint, diffuse glow of objects like DF2.
Right, it just drowns it out. But the Dragonfly telephoto array bypassed this entirely by using refractive optics.
Refractive, so lenses instead of mirrors.
Right. They took commercially available high-end Canon telephoto camera lenses and literally arrayed them together.
It literally looks like the compound eye of an insect pointing at the sky.
It really does. And the reason it works so brilliantly is because those commercial lenses use proprietary nano coatings.
Coatings that were originally designed to reduce glare and ghosting for, like, sports and wildlife photographers, right?
Yes. When you stack dozens of these lenses together, they mimic the light-gathering power of a massive telescope. But because there are no secondary mirrors or central obstructions...
No struts to bounce light around.
Exactly. The internal scattering is suppressed by orders of magnitude. The noise floor just drops out completely, revealing structures that are practically translucent.
Which is incredible. And DF2 was one of those translucent structures.
It was.
It has a physical diameter roughly comparable to the Milky Way, right?
Yeah, it's huge.
But it possesses only about 1/500th of our stellar mass.
It's basically a ghost.
The stars are so sparse, you can actually see background galaxies shining cleanly through the gaps in the galaxy itself.
Which is so visually striking.
But the diffuse nature of the galaxy wasn't the headline here. The headline was, what happened when they pointed the massive Keck telescopes at DF2's globular clusters?
To measure that velocity dispersion we were just talking about?
Right, because globular clusters are incredibly dense, luminous, spherical collections of older stars that orbit the galactic center.
And because they are so bright and compact, they serve as excellent kinematic tracers.
Like tracking lights on a dark highway.
Exactly. By taking spectra of these clusters, astronomers can measure the Doppler shift of their light.
Okay, the Doppler shift.
Yeah, so they can determine exactly how fast those clusters are moving within the gravitational potential of the galaxy.
And the virial theorem dictates that for a galaxy of DF2's size, those globular clusters should be zipping around, governed by the massive dark matter halo we just assume is there.
They should be moving fast. But the spectral data told a completely different story.
They weren't moving fast.
Not at all. The velocity dispersion of those clusters was staggeringly low.
Wow.
It was so low, in fact, that it perfectly matched the gravitational potential of the luminous matter alone.
Just the visible stars.
Just the stars. The stars and clusters were moving sluggishly, exactly as you would expect if there was absolutely no dark matter halo present.
And the reaction from the astrophysics community to that 2018 paper was, well, it was not exactly a quiet round of applause.
Oh, no. It was intense scrutiny.
Bordering on outright hostility from certain corners of the theoretical community, I imagine?
Definitely. And the primary vector of attack was the distance measurement.
Which makes sense. That is the most rigorous and appropriate scientific response, right?
It is. In astronomy, distance is the foundational variable for almost all derived properties. If you get the distance wrong, your entire physical model collapses.
Right, because if DF2 isn't 65 million light years away, but say only 30 million light years away,
then it fundamentally changes what the object is.
It would be intrinsically much smaller, intrinsically much less luminous, and therefore its stellar mass would be drastically lower than they originally calculated.
Exactly. And if the stellar mass is lower, then the sluggish velocity dispersion might actually perfectly align with a normal standard dark matter halo for a dwarf galaxy of that much smaller size.
I see. So the missing dark matter would just be an artifact of putting the decimal point in the wrong place on the distance calculation.
Precisely. The distance debate absolutely dominated the literature for over a year.
I remember that.
Teams ran independent analyses utilizing different calibration methods, specifically looking at surface brightness fluctuations.
What's that?
It's a statistical method for estimating distance based on the pixel-to-pixel variance in the galaxy's light. And some of those initial independent studies suggested DF2 was indeed much closer.
But the Yale team didn't just back down or stand by their initial data blindly, did they?
No, they didn't. They secured highly contested observation time on the Hubble Space Telescope to execute what is really the gold standard of cosmic distance measurement.
The tip of the red giant branch, TRGB.
Yes. The TRGB method is incredibly elegant.
Walk us through how that works.
So when a medium-mass star exhausts the hydrogen in its core, it expands into a red giant, right? It starts burning hydrogen in a shell around an inert helium core.
Okay.
As the core contracts and heats up, it eventually hits a critical temperature and pressure where the helium rapidly ignites.
That's the helium flash.
Yes, the helium flash. And that flash, that specific evolutionary phase, happens at a highly predictable, standardized intrinsic luminosity.
So it functions as a standard candle.
Precisely. Because we know the exact intrinsic absolute magnitude of a star at the tip of the red giant branch. If we can individually resolve those specific stars in a distant galaxy
and measure their apparent brightness from Earth,
then the inverse square law gives us a highly precise, unambiguous geometric distance.
But it takes an incredible amount of resolving power to isolate individual red giant stars in a galaxy millions of light years away.
It's incredibly difficult, but Hubble did it.
Of course it did.
They isolated the TRGB for DF2, and the results were absolutely definitive.
The distance was correct.
It was correct. It was roughly 22 megaparsecs away. It was exactly as large and as massive as the Yale team originally claimed, which meant the velocity dispersion was genuinely anomalous.
The dark matter was truly missing.
It was really missing, and that confirmation was immediately followed in 2019 by the discovery of DF4.
A virtual twin to DF2.
Exactly. Located in the same NGC 1052 group, exhibiting the exact same missing dark matter profile.
Two impossible structures. Which brings us to the April 2026 breakthrough, DF9.
The newcomer.
Right, the third ultra-diffuse galaxy in this specific system, devoid of dark matter. But what elevates DF9 is the sheer precision of the kinematic data they acquired and the spatial relationship it shares with the other two.
The data on DF9 is just beautiful.
Let's look at the instrumentation first, because they utilize the Keck Cosmic Web Imager, or KCWI, on the Keck telescope. How did this instrument pull the velocity dispersion out of DF9 so precisely?
KCWI is a spectacular piece of technology. It is an integral field spectrograph, or IFS.
How is that different from a normal spectrograph?
Well, traditional spectrographs require you to place a narrow slit over a specific part of a galaxy, so you only get kinematic data for that tiny sliver.
Oh, I see.
Yeah. If you want to map the whole galaxy, you have to move the slit, take another long exposure, move the slit again, and basically piece it together over countless nights of observation.
Which is incredibly inefficient for a massive diffuse object where the light is already so spread out.
Exactly. It would take forever. But an integral field spectrograph like KCWI uses an image slicer.
An image slicer.
Yeah, it takes the two-dimensional image of the entire galaxy, optically slices it into dozens of thin strips, aligns those strips end-to-end into one giant pseudo-slit, feeds that light through the spectrograph grating, and then computer software reconstructs it into a 3D data cube.
The data cube.
Right. Two axes represent the spatial X and Y coordinates of the galaxy, and the third axis represents wavelength.
So for every single pixel in the image of DF9, you get a full spectrum of light.
Every single pixel, you can see exactly what elements are absorbing light and how fast that specific patch of stars is moving.
That's amazing.
It is. And they are looking very closely at absorption lines, specifically things like the calcium 2, H, and K lines, or the Balmer series of hydrogen.
Okay, so when we talk about measuring velocity dispersion here, we aren't just looking at the overall redshift of the galaxy moving away from us due to cosmic expansion?
No. We are looking at the Doppler broadening of those specific absorption lines.
The smearing of the fingerprint, basically.
Exactly. The smearing. In a galaxy with a high velocity dispersion, some stars are orbiting rapidly toward our line of sight and their light is blue shifted.
Right.
Other stars are orbiting rapidly away from us and their light is red shifted. Because we can't resolve every single star individually, all their light blends together.
So the sharp, narrow absorption line of calcium becomes mathematically broadened. It gets fat and smeared out.
Yes. So if you measure the width of that absorption line, it tells you the spread of velocities within that population of stars.
The fatter the line, the higher the velocity dispersion, the more massive the dark matter halo must be to contain them.
You've got it perfectly. And the data from KCWI on DF9 was stunning. They calculated the total stellar mass of DF9 to be approximately 1.4 times 10 to the 8th solar masses.
Around 140 million suns.
Right. And based on standard lambda CDM scaling relations, a dwarf galaxy of that stellar mass residing in a typical dark matter halo should exhibit a velocity dispersion of approximately 27 kilometers per second.
So the absorption line should have a very specific calculated width corresponding to 27 kilometers per second.
Yes. But when they processed the data cube from Keck,
What do they see?
the absorption lines were incredibly narrow. The measured velocity distortion was approximately 6.4 kilometers per second.
6.4 compared to the expected 27.
Yeah.
Kinetic energy is just gone.
It is a profound deficit, even pushing the margins of error to their absolute limits, which maxed out around 10.4 kilometers per second, depending on the specific Bayesian modeling framework they applied.
Even at the absolute maximum of the error bar.
It still falls catastrophically short of the expected dark matter profile. a velocity dispersion of 6.4 kilometers aligns perfectly, almost uncomfortably so, with the gravitational potential calculated from the luminous stellar mass alone.
So 140 million solar masses of stars and gas generates just enough gravity to support stars moving at 6.4 kilometers per second.
Exactly.
The math closes without needing any invisible scaffolding. The dark matter is entirely absent.
Which forces us to address the geometry of the situation, because now we have DF2, DF4, and DF9.
3 of them.
3. But they aren't randomly distributed around the central elliptical galaxy. They are aligned along a distinct spatial linear trail.
They form a line, a cosmic breadcrumb trail spanning over 2 megaparsecs, which is what, roughly 6.5 million light years in length?
Yes. And that linear alignment is the critical piece of forensic evidence here.
Why is the line so important?
Because it completely eliminates the possibility that these are primordial anomalies that just, coincidentally form without dark matter halos. The linear structure strongly implies a highly directional, violently dynamical origin.
We are looking at the splatter pattern of a cosmic car crash.
A very messy car crash.
Specifically what astrophysicists refer to as a bullet dwarf collision.
Right. The terminology is a direct nod to the famous bullet cluster, which was a much larger scale collision between 2 massive galaxy clusters that provided some of the earliest empirical evidence for the separation of dark and baryonic matter.
Oh, interesting.
What we are seeing in the NGC 152 group is that exact same physical process, but scaled down to the interactions of individual dwarf galaxies.
I want to really dig into the hydrodynamics of this collision because my initial intuition when I hear galaxies colliding is heavily biased by images of, like, the antenna galaxies or the impending Milky Way Andromeda merger.
Beautiful, slow gravitational dances.
Exactly. I picture this slow, billions of years long gravitational ballet where tidal forces stretch the galaxies out, their gas clouds tangle together, and eventually they coalesce and merge into one larger unified system.
Right.
But that model doesn't explain the creation of a linear debris trail completely stripped of dark matter.
No, it doesn't, because your intuition is describing a low-velocity collision, which is indeed how the vast majority of galaxy mergers occur.
Okay.
The relative velocities in those typical mergers are lower than the escape velocity of the combined system, so they are gravitationally bound to eventually merge.
They can't escape each other.
Right. But the bullet dwarf scenario is an entirely different kinematic beast. We are talking about a high-velocity, highly supersonic, potentially head-on collision.
How fast?
The relative velocity of the 2 progenitor dwarf galaxies exceeded their mutual escape velocity. We're talking hundreds of kilometers per second.
So they aren't merging, they're glowing right through each other.
They're passing right through one another. But the interaction fundamentally alters their composition due to the radically different physical properties of the matter involved.
This is where it gets so weird.
It really does. We have to separate the galaxies into 2 distinct components. The collisionless N-body system.
Which is the dark matter and the existing stars.
Yes. And then the collisional fluid, which is the interstellar gas.
Okay, let's start with the dark matter halos. 2 massive, invisible gravitational wells rocketing toward each other at perhaps 300 to 400 kilometers per second. When they intersect, what actually happens physically?
Well, dark matter is essentially collisionless. It interacts almost exclusively via gravity. It doesn't possess electromagnetic charge, so it doesn't experience friction or fluid dynamics or ram pressure.
So it doesn't hit anything.
Exactly. When the 2 dark matter halos overlap, the individual dark matter particles simply pass right through each other.
Like ghosts.
Like ghosts. Their trajectories might be slightly perturbed by the shifting gravitational potential, sure, but they do not physically collide or slow down.
The invisible scaffolding of the first galaxy just ghosts straight through the invisible scaffolding of the second galaxy.
Precisely.
They cross the intersection and keep moving at almost their original velocity.
Mm-hmm.
And the existing stars in those dwarf galaxies behave the exact same way.
They do. Because the space between stars is so vast, the odds of 2 stars physically hitting each other are effectively 0. They act as collisionless particles, too.
So the dark matter halos and the older stellar populations essentially fly straight through the impact zone and continue on their way, largely intact.
Largely intact, yes, but forever altered by what they leave behind.
Because the interstellar medium, the vast clouds of cold hydrogen and helium gas, experiences a drastically different reality in that intersection.
A much more violent reality.
Oh.
The gas is baryonic. It is a physical fluid.
It's highly collisional.
Extremely collisional. When these massive gas clouds moving at hundreds of kilometers per second smashed into each other, they generate immense ram pressure.
Like a high-speed car crash.
Exactly.
Right.
And the collision is highly supersonic because the relative velocity of the impact drastically exceeds the internal sound speed of the cold interstellar gas, which might only be, 10 kilometers per second.
So they hit, and it triggers a massive system-wide shock front.
A brutal shock front. The kinetic energy of the forward momentum is instantaneously converted into thermal energy through shock heating.
Things get hot fast.
Very fast. The gas temperatures spike to millions of degrees, radiating away energy via Bremsstrahlung or free emission. But mechanically, the critical factor is that the ram pressure completely halts the forward momentum of the gas. The physical gas clouds slam into each other, compress violently, and come to a dead stop right in the center of the impact zone.
Wow. So the gas hits a brick wall, while the dark matter halos, being collisionless, just keep flying.
They just keep going.
The gas literally gets ripped out of its own gravitational potential well. The dark matter ghosts drive away, leaving the entire physical payload of gas dumped at the intersection.
It is a complete violent decoupling of baryonic matter from dark matter.
That is insane to picture.
It's incredible, and as the dark matter halos continue moving apart, the immense volume of shocked, compressed gas left behind in the intergalactic medium begins to cool.
And as it cools, it loses pressure support, allowing gravity to take over.
Yes, but, and this is the crucial part, this gravity is entirely different now. It isn't being guided by a massive dark matter well anymore.
Because the well left.
Exactly. The well is gone. The gas has to rely purely on its own self-gravity.
Which usually isn't enough to form a galaxy, right?
Normally, no. To collapse and form stars without the deep potential well of a dark matter halo, the gas must exceed the Jeans mass limit under its own weight alone.
Okay, the Jeans mass.
Yeah, it's the critical mass where gravity overcomes internal gas pressure. Because the collision compressed the gas so violently, it achieves the extreme densities required to trigger gravitational collapse on its own.
The shock wave forced it past the limit.
Exactly. The gas fragments and ignites, triggering a massive, rapid starburst event along this 2 megaparsec debris trail.
And because it is forming stars entirely out of that orphaned compressed gas, the resulting galaxies, DF2, DF4, and DF9, are born completely naked.
Completely naked.
They are entirely devoid of dark matter from the very moment of their creation.
They condense directly out of the cosmic shrapnel, and this specific hydrodynamical mechanism elegantly explains the other highly unusual features of these galaxies, too.
Like the globular clusters. You mentioned earlier that their globular clusters are bizarre.
Yes. The globular clusters in these galaxies are significantly more luminous and massive than the clusters we find in standard dwarf galaxies of similar mass.
Why is that?
That is a direct signature of the high-pressure environment of the post-collision gas. In a standard dwarf galaxy, star formation is a relatively slow, inefficient process regulated by the depth of the dark matter well and, supernova feedback.
Right, to slow burn.
But in the bullet dwarf scenario, you have a massive reservoir of gas that has been shock compressed to extreme densities.
So it all collapses at once.
Yes. When it collapses, it does so violently and efficiently, forging these overmassive, incredibly dense globular clusters all at the same time.
It's like comparing diamonds formed slowly deep in the earth to diamonds forged instantaneously by the explosive pressure of a meteorite impact.
That captures the physics perfectly. It's an explosive formation. Furthermore, because this was a single violent starburst event that exhausted or expelled the remaining cold gas rapidly, these galaxies are now entirely quiescent.
Meaning they aren't actively forming stars anymore.
No, they are just aging, quietly drifting along this linear trail, populated by older, cooler stars. Everything we observe in DF9 flawlessly matches the predictive models of a high-velocity, dark matter-stripping collision.
The forensic reconstruction of the bullet dwarf collision is just incredible.
Right.
It paints a picture of a universe that is highly dynamic and, frankly, deeply violent.
It's a messy place.
It really is. But the significance of DF9 extends far beyond just explaining how a weird, linear trail of galaxies formed. This specific discovery is fundamentally altering the landscape of theoretical physics.
Specifically regarding the most persistent debate in cosmology.
Exactly. Does dark matter actually exist as a physical particle, or is our math just wrong?
It is the absolute crux of the issue. The existence of DF9 serves as a highly robust observational falsification of alternative gravity models.
To understand why finding a galaxy without dark matter proves that dark matter is real, we really have to examine the mathematical architecture of the alternative. Modified Newtonian dynamics, or MOND.
Let's really dig into MOD. Because it's easy to dismiss it as a fringe theory, but mathematically, it was a highly elegant, deeply reasoned response to the rotational curve problem we discussed earlier.
Right. If you look at the history, physicists were faced with a tough choice. Either the universe is filled with a ghost particle that we cannot interact with, cannot directly detect in any collider, and cannot observe despite decades of highly funded, incredibly sensitive underground experiments. Or Isaac Newton's gravitational equations just need a slight adjustment when applied to galactic scales.
Which is an entirely valid scientific hypothesis. It was first proposed by Mordechai Milgram back in 1983.
And what's the core idea of MOD?
The foundation of MOD is based on the observation that the discrepancies in galactic rotation curves do not randomly appear based on the size or mass of the galaxy.
Right.
Rather, they appear specifically when the gravitational acceleration drops below a certain critical threshold.
This is the A0 parameter, right?
Exactly, the A0 parameter. Milgram proposed a fundamental constant of acceleration, a zero, which is roughly 1.2 times 10 to the negative 10th meters per second squared.
Which is an incredibly small acceleration.
Tiny. MOND posits that in regimes of high acceleration like our solar system, or the dense inner cores of galaxies, Newton's law of universal gravitation, where the force of gravity drops off with the square of the distance, holds perfectly true.
So the math we use to send probes to Mars or calculate the orbit of the Earth remains completely unchanged.
Yes. Unchanged. But MOND theorizes that when you move to the extreme outer edges of a galaxy, where the gravitational pull from the central mass becomes incredibly weak and the acceleration drops below that a zero threshold.
The laws of physics change.
Exactly. Gravity stops behaving according to the inverse square law. Instead, it transitions to a regime where it drops off linearly. It scales as 1 over r instead of 1 over r squared.
Which means gravity becomes stronger, relatively speaking, over vast distances than Newton predicted.
Precisely. It modifies the Poisson equation. By tweaking how gravity behaves at extremely low accelerations, MOND mathematically perfectly reproduces the flat rotation curves of spiral galaxies.
And the high-velocity dispersions of dwarf galaxies.
Yes, it explains the missing mass problem without needing to invent a single new particle. The extra gravity isn't coming from dark matter. It is baked into the fundamental geometry of space-time at those specific accelerations.
Okay, but if MOND is a fundamental law of physics, it has to be universal, right?
It must.
It must apply to every object in the universe experiencing low acceleration. Which brings us right back to our anomalous trio in Cetus.
And this is exactly where the MOND framework encounters a critical structural failure, because ultra-diffuse galaxies like DF2, DF4, and DF9 are so physically sprawling, and their stellar mass is so low, their internal gravitational accelerations are incredibly weak.
So the entirety of DF9 exists deep within the low acceleration regime, well below the A0 threshold.
Below it.
Which means, under the rules of MD, DF9 should be fully experiencing this modified, stronger version of gravity.
Yes. According to MOND, the velocity dispersion of DF9 should be artificially high, driven by the modified laws of physics. It should exhibit the exact same kinematics as a dark matter-dominated dwarf galaxy.
The stars should be moving fast.
Fast, yes. But the KCWI data showed us unequivocally that they are not.
They are moving at 6.4 kilometers per second.
They are behaving exactly, perfectly according to standard, unmodified Newtonian dynamics.
Wow.
The fact that DF9 obeys purely Newtonian kinematics in a regime where MOND predicts it shouldn't completely breaks the universality of the MOND hypothesis in this context.
I'm trying to visualize this tension because it feels like a massive philosophical shift. If MOND were true, it's almost like, imagine gravity is the atmosphere.
Okay, I'm with you.
And we keep seeing these empty three-piece suits walking down the street, completely upright, holding their shape as if a person is inside them. MOND theorists look at the empty suits and say, there's no invisible man. The fundamental laws of aerodynamics in this specific neighborhood dictate that empty suits are supported by air pressure and forced to walk upright. The atmosphere is just modified here.
That captures the deterministic nature of MOND perfectly. The environment dictates the behavior.
Right. But then we look at DF9. We see an empty suit crumpled on the sidewalk, not moving, obeying normal, unmodified gravity, right in the middle of that exact same neighborhood. If the atmosphere itself was fundamentally modified to hold suits upright, that suit on the sidewalk should be walking too. But it's not.
Which means the law of aerodynamics isn't modified.
Exactly. The fact that the suit is crumpled on the ground proves that the other suits walking down the street aren't being held up by a modified atmosphere. They're being held up by invisible men.
I love this analogy.
And we just happen to find the one suit that the invisible man took off and left behind. DF9 is the crumpled suit. It proves that dark matter isn't a fundamental, baked-in modification of how gravity works across the universe. It proves dark matter is a distinct, physical, separable substance.
Yes.
You can take it away from the baryonic matter, and the baryonic matter reverts to standard Newtonian behavior.
That is an absolutely brilliant synthesis. The separability is the ultimate proof. Dark matter is an isolatable component of the universe.
It's a real thing.
It is. Now, to be rigorous, we really must acknowledge how the MOND community has attempted to address this. They have proposed something called the external field effect, or EFD.
Oh, I was wondering about that.
Yeah.
Because theoretically, MOND allows for a loophole if a massive external object is nearby, right?
Yes. The external field effect posits that if a low acceleration object, like our dwarf galaxy DF9, is deeply embedded in the strong gravitational field of a massive neighbor.
In this case, the giant elliptical NGC 10052.
Right. The external acceleration can override the internal MOND dynamics. Essentially, the strong background gravity of the giant neighbor pulls the dwarf galaxy back into the Newtonian regime.
It violates the strong equivalence principle, but mathematically it offers a defense. So does the EFE save MOND in the case of DF9?
It requires extreme fine-tuning. For the external field effect to perfectly cancel out the MOND behavior and result in the exact 6.4 kilometers velocity dispersion we observe, DF9, DF2, and DF4 would have to be situated at highly specific, precise distances from the central elliptical galaxy.
Like incredibly lucky positioning.
Yes. But our 3D spatial modeling of the NGC 1052 group suggests they are not deep enough within that potential, for the EFE to fully explain the discrepancy without stretching the parameters to their absolute breaking point.
It requires too many coincidences.
Exactly. While the debate will certainly continue in the literature, the consensus forming around the bullet dwarf collision model provides a naturally occurring, hydrodynamically sound mechanism that elegantly explains every observed anomaly of these galaxies without needing to invent complex loopholes in modified gravity.
Right, the physics just works.
DF9 strongly reinforces the lambda CDM model. Dark matter is real. It just isn't there anymore.
This totally rewrites the textbook on galaxy formation channels, honestly.
Yeah.
We've always assumed that dark matter halo was the absolute prerequisite, the required foundation before you could pour the concrete of a galaxy.
The required starting point.
Yeah. DF9 proves you can build the house without the foundation, provided the materials are subjected to enough trauma.
That's a good way to phrase it. It introduces collision-induced dwarf galaxies as a distinct, viable evolutionary path.
So with this new framework established, what is the astrophysics community doing right now? Where does the cosmic laboratory go next?
Well, the mobilization is happening across multiple domains, observational and theoretical. On the observational front, these objects are now absolute prime targets for the James Webb Space Telescope.
Oh, of course, JWST.
Yeah. While Keck provided incredible kinematic data, JWST's near-infrared camera in IARC-CAM and its near-infrared spectrograph NRSpec offer unparalleled capabilities to resolve the individual stellar populations deep within DF9.
Because we want to forensically date the collision, right? We know it happened roughly 8 billion years ago, but JWST can tighten that timeline.
Dramatically. JWST can map the asymptotic giant branch stars and precisely measure the metallicity.
Metallicity being the ratio of heavy elements like iron to hydrogen.
Right, denoted as Fe/H. They will also look really closely at alpha element enhancements.
What does that tell us?
So when that violent starburst occurred post-collision, the massive short-lived stars exploded as core collapse supernovae, right?
Yeah.
And those supernovae enriched the surrounding gas with alpha elements like oxygen and magnesium very rapidly.
Oh, before the lower mass stars had time to evolve and produce iron.
Precisely. By measuring that specific chemical abundance ratio, JWST can pinpoint not just the age of the stars, but the exact duration and intensity of the starburst event.
That's incredible.
It will tell us exactly how fast that collision compressed the gas and how rapidly the star formation quenched afterward.
And beyond deeply analyzing the three we have, the hunt has to be scaling up to find more, right?
Yeah.
A 2-megaparsec debris trail has to contain more surviving fragments.
Oh, the search space is vast.
Yeah.
But we are entering the era of extreme wide-field surveys. The Vera C. Rubin Observatory, conducting the Legacy Survey of Space and Time, or LSST, is going to be revolutionary here.
With its, 3.2 gigapixel camera?
Yes. It will repeatedly image the entire visible sky, specifically optimized to detect the incredibly faint, low-surface brightness universe that traditional surveys just miss.
It will map the diffuse structures that are essentially invisible to us right now.
It is highly probable that the Rubin Observatory will identify extended tidal features, fainter stellar streams, and potentially dozens of smaller dark matter-free fragments scattered along the NGC 1052 trail.
And when Rubin identifies those candidates,
then the massive ground-based telescopes, the extremely large telescope currently under construction, and the very large telescope will follow up with high-resolution integral field spectroscopy to confirm their missing dark matter profiles.
so we're basically building a pipeline to find these ghost galaxies.
Exactly, a dedicated pipeline.
And while the observers are mapping the sky, the theorists have to be running supercomputer simulations to see how often this actually happens. Because a bullet dwarf collision seems like an insanely specific alignment.
It does seem rare, and the theoretical teams are heavily invested in running advanced hydrodynamical simulations right now. These are incredibly computationally expensive, by the way.
I can imagine.
You can't just run an n-body simulation model in gravity alone. You have to run Eulerian grid-based codes or smooth particle hydrodynamics to accurately model the shock heating, the ram pressure stripping, and the radiative cooling of the gas simultaneously with the collisionless dark matter.
So they're building digital models of the collision, tuning the knobs, changing the impact parameter, adjusting the relative velocity to 300 or 400 kilometers per second, altering the initial gas fraction of the dwarf galaxies, just to see exactly what initial conditions yield a DF9.
Yes, they're playing with all the variables. And the overarching goal of those simulations is to determine the statistical frequency of these events across cosmic time.
Is the NGC 152 system a once-in-a-universe anomaly?
Right. Or, because the early universe was much denser and interactions were more frequent, were these high-velocity, dark matter stripping collisions relatively common?
Wow. If they were common, there could be a massive hidden population of dark matter-free galaxies out there, fundamentally challenging our senses of the cosmos.
It's a very real possibility.
It forces us to reevaluate how much of the universe is pristine and how much of it is actually just surviving wreckage.
It really does.
It has been an intensely complex narrative to untangle today. We started by examining the mathematical tension inherent in the virial theorem, the requirement for dark matter to stabilize the high-velocity dispersions observed in galactic structures.
Right, the invisible seatbelts.
We then tracked the forensic data from the low-surface brightness imaging of the Dragonfly array to the highly contested distance measurements utilizing the tip of the red giant branch, and ultimately the definitive Keck integral field spectroscopy that recorded DF9's anomalous 6.4 kilometer per second velocity dispersion.
And we move from observing the anomaly to uncovering its violent origins.
The bullet dwarf collision.
Yes. The hydrodynamics of the highly supersonic bullet dwarf collision demonstrated how collisional baryonic gas can be violently shock-heated and entirely stripped away from its collisionless dark matter halo, collapsing under its own immense pressure to forge massive globular clusters and dark matter-free galaxies.
And finally, we synthesized how that dynamical separation serves as the definitive counter-argument to modified gravity theories like MOND.
The crumpled suit.
The crumpled suit. By demonstrating that DF9 behaves precisely according to Newtonian dynamics in a low acceleration regime, it isolates dark matter as a distinct physical entity that was dynamically left behind, not a universal modification of gravity.
It is a profound demonstration of the scientific process, really, where a singular anomalous observation forces a comprehensive reevaluation of both theoretical physics and our models of galaxy formation.
As we conclude this exploration, I want to leave you contemplating the structural reality of the night sky. For decades, we have looked up and assumed a universal uniformity, that every glowing collection of stars is cradled securely within a massive, invisible gravitational well.
The standard model.
Right. But DF9 and its siblings along that violent 2-megaparsec trail shatter that assumption. They are architectural impossibilities that survive the cataclysm.
They are the exceptions that prove the rule.
Exactly. So the next time you observe the deep sky, consider the invisible violence required to forge it. How many other seemingly serene, quiescent galaxies drifting through the void are actually completely hollowed out?
Ghost towns.
Ghost towns. How much of the universe's quiet beauty is actually composed of the faint, orphan shrapnel of ancient invisible collisions? How many massive houses are floating out there perfectly intact, entirely missing their invisible columns, waiting to be found?